Okay, guys. So this is going to be lab for this week is the speed of light. So using what we'll call the Foucault setup, um, we're going to do the same experiment that he did in the late 1800s in order to determine the speed of light. So the speed of light is obviously a very important and fundamental constant. It sets the speed limit for the universe. Nothing can go faster than the speed of light. And because it is so fundamental and it's used in so many areas of physics, it becomes even more important that we are able to obtain an accurate number for it. So this is just one method that we'll be able to use in order to get an experimental value for the speed of light. It involves a series of optics, so a series of rotating or a rotating mirror, a series of lenses, and a fixed and a beam splitter, or basically all of the components. So what we have here in the top, we'll ignore what's going on down here for in the bottom for a second. What's going on here at the top is just a really rough sketch of what's happening. So the light is going to come from the laser, be focused by a lens that we'll label L1. It'll go from this lens to a beam splitter. This beam splitter has a partially mirrored surface on the left-hand side, so it allows light that's going from right to left to pass completely through it. So this light just continues through this beam splitter as it's going from right to left, right? It goes through this second lens, which will straighten the light back out. We'll call that lens L2. It'll hit this rotating mirror. So this is what we'll call MR, the rotating mirror. And it'll hit that, and then it'll come over and it'll strike a fixed mirror that we'll call MF, some distance D away. Right, and this is not drawn to scale, right? This distance from the rotating mirror to the fixed mirror is actually very large, right? So this mirror would actually be located way over your past on the other side of the laser, and you'll see this whenever we go through this in the next part, and whenever I demonstrate in lab. So this is just the basic setup. It kind of allows you to see what's going on. So, and so whenever the light comes here and hits the fixed mirror, it'll travel back to the rotating mirror, go back through this lens L2, in which case it'll hit the left-hand side of this beam splitter, and then some of that light will then be reflected into a viewing area that we'll be able to then use to measure the position of our object. Our image. Okay, so we'll have some object on our mirror here, and we'll be able to, from that object distance, be able to determine what this image distance is, or actually vice versa. From this image distance here, we'll be able to determine what this object distance, or the distance that this moves whenever we rotate this mirror. Okay, so this is just a way of being able to view what's happening on the mirror over here. Okay. So this is kind of what's happening on a kind of a more accurate scale. So we have our beam coming through. It gets focused here, right? This distance here we'll call F1, which is the focal length of lens 1. So this distance F1, so it'll be focused here at this point. This is where our image will be located. It'll continue on through the beam splitter, as we already talked about. It just goes straight on through this lens over here, which I've drawn awfully. Then realigns these lines, right? So that it then strikes this rotating mirror, and then it is then reflected onto our fixed mirror. So let's just label some important distances that we're going to be using later on, and you'll see why these distances become important as we go. So we'll label this distance from L2 to the rotating mirror as distance B. We already know this distance here from this rotating mirror to our fixed mirror. That's distance D. And then we'll also have a distance L, which will be from one of these mirrors, or one of these lenses, to the other lens. We'll call that L. So those are some important distances, and it'll become apparent in a second why that is. But basically, the point of this setup is we can use the rate at which this mirror changes and the position of this image that we'll see here in order to determine our speed of light. So we can change the rate at which we spin this mirror. We can then measure the change in position of the image, which corresponds to a change in position of this object height over here. And from that, we can then calculate the speed of light. So to do this, we need to come up with an expression for the change in theta. Okay. And this is the change in angle that this rotating mirror moves from the time that light strikes it to the time that light gets back to it. Okay, so change in theta is light comes in, strikes off, comes back, and by the time the light returns to this mirror has rotated an angle of delta theta. Okay, and we want to come up with an expression for that delta theta, and it'll be related to the speed of light, as you'll see here in a second. So let's find out how are we going to find this value here. So if we draw, let's move this up, and if we draw what happens initially, so our light comes in and strikes our mirror. So we have our light coming in, striking this mirror. Let's say this is our normal line. Let's say this angle that it's striking it is theta, which is equal to the angle of rotation of this mirror. Our reflected light is going to come off at an angle equal to our incident angle. So this is also going to be theta. Okay, and so we couldn't call this entire angle here, which is the initial angle, we'll call this 2 theta, and we'll set that to our initial angle theta naught. Right? It's the initial angle between our incident and our reflected beam. Okay, now at some later time, right, so we still have this light incoming here, but our mirror has now rotated an additional delta theta. So it's now rotated an additional amount of degrees. So here's our normal, okay? And now this angle here is now theta plus delta theta, because now we've rotated an additional amount, delta theta. Okay, that means that our outgoing or our reflected beam is also going to have theta plus delta theta. All right, so that means this total angle here is going, we'll call this theta 1, and it's going to be equal to 2 times theta plus delta theta. Okay? And now the reason that I'm getting these two angles is because what I want here is if we have our angle, or if we have our two beams, so this one would be our incident corresponding to this reflected beam, and then this one will be our this will be our first reflected beam, and then this will be our second reflected beam at some time later after the mirror has rotated, right? And it's striking this spherical mirror, or the fixed mirror, some distance d away, right? And then this is right here. So this angle here, right, is our initial angle, theta naught, and then this angle here, this total angle, is theta 1. And so we want to know what the position is of this spot, or how much has this spot moved from this position to this position. So we want to know this distance, which is this arc length, right? And the position, the change in position of as this beam moves from here to here is what we'll call the object height. All right. So if I want to find out what this object height is, and relate it to this delta theta, I have to just use the fact that this is an arc, then it has an angle equal to this angle here that we'll call theta 2. Right, so if I want to know the distance h naught, and this is just the equation for the length of an arc, right, or the equation for arc length. So this arc length h naught is going to be equal to d times theta 2, and theta 2 is just equal to the difference of theta 1 and theta naught. Theta 1 and theta naught, those are these two angles that we've already found over here. So if we continue to write this as d of 2 theta plus 2 delta theta, and then minus 2 theta, right? That's going to be equal to just 2d delta theta. Okay. So we have an equation for delta theta, and we have an equation for h naught, but we still don't have c. Okay. So let's also come up with an equation for delta theta that's related to c, and then we'll plug it into here. So what I can do is I can say that delta theta is going to be equal to, whatever the speed that the mirror is rotating, so some angular speed, times the interval of time that it takes to rotate this amount of degrees, right? And so if we rewrite time in terms of the distance over the velocity of the light, the distance that the light travels in this time, or during this time where delta theta is happening, is going to be 2d. So time is equal to distance over velocity. So the distance that it travels is 2d because it goes to and from the fixed mirror by the time that the mirror has rotated an additional delta theta degrees, right? And then we divide that by the speed at which the light travels, which is c, which is what we want. Okay. And now if we take this delta theta and plug it in over here, we'll get another expression for h naught, which ends up being equal to it'd be 4d squared omega over c. All right, so d we know, it's just a distance. Omega we can control, we'll be able to control the speed. C is what we want, but we still don't have a way of measuring h naught, or the object height, ho, right? And so before I told you that the ho over here on this or our object over here, our object height, is related to our image height that we'll be able to view in our viewing screen, all right? And they're related by a magnification equation. So it turns out that the magnification using this thin lens setup is going to be equal to whatever the image height is divided by the object height, which also turns out to be equal to the negative of di over do, where di is the distance from the image to L2, and do is the distance from the object to the lens L2. Okay, so we can rewrite di, right? If di is the distance from L2, which is here, to this image here, right, we can see that that distance is going to be L minus F1, right? This distance here is this distance minus that. So di is L minus F1. And do, or the object distance, is going to be equal to, it's going to be the distance from the mirror to L2. So it's d plus b. So we have d plus b. All right, now using these three equations, this guy, and this guy, and combining them and solving for c, what you'll end up getting is the final equation that we'll use in this lab, which is equal to 4 omega d squared L minus F1 divided by hi d plus b. Okay, so this is the equation for the speed of light. So we know we can control everything in here, right? F is a constant, L is a constant, D is a constant, B is a constant. They're just all of these distances. Hi will be able to measure, and we'll be able to measure it at varying speeds of our mirror. So what we'll end up doing here is you'll graph, we'll have these positions, hi, and this is actually going to go in both ways because we're going to spin the mirror clockwise and counterclockwise. So we'll have negative frequencies and positive frequencies, okay? And so you'll get a graph that looks something like this. And then from this line, that'll look like that, we can then be able to determine slope. So you'll have to rearrange this equation so that we get hi by itself, omega will be x, and everything else, right, everything else in that equation will be equal to this slope. So you will need to find out what that is, right? The slope is, like, this is a common occurrence. Sorry, guys. There we go. So the slope will be some combination of whatever is left over after you've put it into linear form, right? So the slope here is not just equal to c. So you'll need to find out what this expression for slope is using this equation and then putting it into the correct form. Okay, so in the next part, we'll be in lab, and then I'll go through how are we going to go about determining what these positions or what these distances HI are. And then once you get that, it's as simple as just graphing the positions versus the frequency that we're spinning it at, and then finding the slope, and then from that slope in this equation here, calculating C. Okay, see you in lab. Okay guys, here we are in lab for the speed of light lab. So here we can see the apparatus for this lab. So all of this should look familiar from the picture, hopefully. This is our laser, right? That's our shooting the laser through. This is our L1, which is our first lens. This is our viewing screen, and you can see up here is where we would look through to be able to see the position. Here we can see a micrometer, and we can turn this micrometer, and that'll allow us to measure the position of the dot or of the image that we'll see in here, and we'll show you that after we show you this apparatus. This is L2 over here, so this is our second lens, and then finally way over here is our rotating mirror. If we look at the control for the mirror, I can set the stop, and right now it's set to be 750 hertz, and I can change that. I can change the speed, and I can also change the direction that it spins by hitting this button here. So if I want, it's going clockwise now. If I wanted to change it to go clockwise, I hit that button, and then if I want to ramp it up to its maximum speed, I can hold that button down, and then it'll ramp up to its maximum speed. Okay, so, and then if you're wanting to see the rotating mirror, that's it in there. Okay, let's stop that. So yeah, so it's coming from the laser here, through all of these optics which have already been aligned. So if you're interested in knowing how these were aligned, you can read through the manual. Basically, it involves shining this light through some pinholes, and then using these screws at the base, at the center, and at the end over there to adjust the height, and so we can level out the whole apparatus so that the light just goes straight to the mirror. And then we have to take the light from this mirror and shine it across the room, way over there. We can walk over there and see. That's where our fixed mirror is, our fixed spherical mirror. So way over here is where our fixed mirror is, about probably 10 to 15 meters away from the rotating mirror, right? So it's coming from way over there, bouncing off, and then coming back to the apparatus, which will then re-strike this mirror, pass back through this, and then go into the beam splitter and then up, and then we can then view it. All right, so what I'm gonna do now is try to see if I can get the camera aligned with the eyepiece and see if we can actually see the image, see what's going on inside of this viewing screen. And then if we can see that, then we can explain how you're gonna actually go about finding the different image heights at the varying speeds for the rotating mirror. All right, so I will be back once I get this all aligned with that viewing screen. Okay guys, so we got it finally lined up with the eyepiece here. So let's go ahead and turn on our mirror. We'll start spinning it in the counterclockwise direction. And this will be at 750 hertz. And we can see as it comes up to speed, you can see that spot start to move. And then if we look at the crosshairs, I can change the position of those crosshairs by adjusting the micrometer. So as I move the micrometer, you can see those crosshairs will move within the viewing area. So I can then be able to measure the top of the beam or the center or the bottom, right? And we'll be able to get those positions. So this is at 750 hertz counterclockwise. So if I wanted to find the position of this, it's hard to say exactly where the center is. So what you'll see in your data sheet is there will be series of points, and there will be a top point. So we'll take the position at the top, and then we'll come down here and then read the micrometer and take the position at the bottom. And then the average of those two positions will give us the position at the center of that spot. All right, so that's how we'll be able to get these positions using the micrometer at the various frequencies. So let's go ahead and up our frequency up to its maximum value. You'll see that that dot starts to move upwards. And once it finally comes up to speed, we would then be able to again measure the new position. So again, we would move our crosshairs until it gets to the bottom of that spot, take our position off the micrometer, move to the top of that spot, take our position again, and then the average of those two positions will give us our HI, or the image height, which will be the position at the center of that spot. All right, let's go ahead and turn our speed off, our mirror off. And then we'll go ahead and change the direction and see how does the direction affect how the spot moves. So we'll go clockwise now. So we should see our spot in our viewing screen here. There we go. There it is. So this is at 750 clockwise. So we can, again, take our position the same way that we took the other two positions, just measure the position at the bottom and at the top. And then we can also increase our speed here. Let's go ahead and increase it maximum. So this is our maximum speed in the clockwise direction. And we can see that that spot begins to move down. Right, so the position of the spot changes as our it'll go down or up depending on which direction we're spinning, and it'll go more down or more up depending on the speed. So again, we can move our micrometer to be able to move the crosshairs, take the position at the top and at the bottom, take the average to get that center, and then we'll do this for varying speeds. So our rotating mirror controller can set the speed of the mirror to be at varying speeds. So in the data sheet, let's go ahead and turn this off. So in the data sheet, you'll see you'll see clockwise frequencies and counterclockwise frequencies, and the positions for the top and the bottom of the spot. And then from those top and bottom spots, you can then find the average position, which will be your HIs. Okay, so that's how you would have gone about finding these HI positions at varying frequencies had you have set this lab up. So like I said before, getting all of the optics set up in this lab is what would have taken you the longest. Getting this data wouldn't have taken very long. Once you got it set up, it's just a matter of changing the frequency and then taking the positions of the top and bottom of the spot in order to get your HI values. Okay, so yeah, that's the Speed of Light lab. If you have any questions, just let me know. Yeah. Just email me, or we can talk through Zoom. All right, so that's going to be it for the Speed of Light lab.